Well, good morning to you. It's great to see such a good audience. I very, very rarely wear a tie. In fact, I wear it about once a year, and there's a very special reason I'm wearing a tie, for which will be revealed during this talk. So I'm going to talk about radar. I'm going to particularly talk about the history of radar from when it was invented up to the end of the Second World War. And I want to convince you that mathematics, particularly through its use in radar, played a major role in winning the Second World War. So if ever there was an application of maths, this was it. And one of the reasons I'm standing in front of you talking about radar is that before I worked for the University of Bath, I actually worked in radar myself. So this is very much from the heart, this talk. It's combining various interests of mine. So this is going to be what I'm going to tell you about. Last year, in fact, was a very significant year for radar. It was the 75th anniversary, both of its invention, and when I say its invention, I mean its invention in England rather than its invention in Germany or America. Then last year was also the 70th anniversary of the magnetron, which I'll tell you about, the Battle of Britain, which I'll tell you about, and the Tizard mission to the USA. And so the talk I'm going to give, I'll take you a bit from the start, how radar was invented and how mathematics was vital in that invention. If it hadn't been for maths, radar would never have been invented. I'll then tell you how radar was used during, first of all, the Battle of Britain, and then during the rest of the Second World War, and in fact show you the vital role played by the University of Birmingham. It's very important that we're in Birmingham. Without Birmingham, we wouldn't have had radar. So I'll tell you why Birmingham is so important. And then I'll try and tell you where radar has led us on to in terms of modern technology. So as I say, radar started for a mathematical calculation. And the main calculation I'm going to show you is one which was written in 1935, but in a very real sense, radar goes back much to an earlier mathematical calculation which was made in the 19th century. And this was a calculation by a guy called Maxwell, and there he is. Maxwell was without doubt one of the greatest scientists that's ever lived. It's a bit of a shame that he's not as well known as people like Einstein or Newton, because Maxwell was, I say, one of the greatest scientists of the 19th century. Amongst his many achievements were the discovery of radio waves. He also was the person that invented colour photography, and he also invented the governor that was used in steam engines. So he had a lot of sort of good things. But his main achievement was coming up with some mathematics. Now, this is Meet the Mathematicians. Fortunately, the ice has been broken. There's also already some maths on the board. I will be showing some maths in this talk, so I think it's best to brace ourselves when we get complicated formulae. So here's the formula. There we are. This is the formula that Maxwell came up with. And when I was introduced by Michael saying I was chair of maths at the Royal Institution. At the Royal Institution, there was a guy called Faraday, and Faraday did some wonderful experiments on electricity and magnetism, and then he handed over his experimental ideas to Maxwell, and Maxwell turned them into mathematics, and these are the formulae that Maxwell came up with. And then Maxwell looked at those formulae and solved them, and he found that they had a solution which was something no one had ever come across before, what we now call a radio wave. And those formulae predicted radio waves. Without those formulae, we wouldn't have radio. Without radio, we wouldn't have TV. We wouldn't have mobile phones. We wouldn't have Wi-Fi computers. We wouldn't have microwave ovens. We wouldn't have radar. We wouldn't have aeroplanes. The whole of the modern world would not have happened if it hadn't been for Maxwell and those formulae. So I think mathematicians can justly claim to have invented the modern world, and that was the guy that invented them. So radio came out of those formulae. And if you go on to study mathematics or physics or engineering at university, the chances are you'll meet those formulae probably in about the second or third year of your studies. So that was a theoretical prediction. Maxwell was not a practical scientist, although, as I say, he did invent the colour photograph. But he did predict the existence of radio. And then later on, a guy at the top called Hertz actually went on to show with physical apparatus that radio waves existed. And what he did was he took jars, which he covered with metal. He put sparks across the jars. Those jars acted as radio transmitters, and he found he could send sort of messages from one jar to another, from one end of the room to another. And Hertz was a German scientist, and nowadays we have kind of immortalized him by using his name to mean frequency. So when you switch on your radio and it's 101 FM, it means 101 megahertz, and Hertz is his name. And what Hertz did was he showed not only that radio waves existed, but in fact that they bounced off things. He found if you put metal objects, then the radio waves would bounce off those metal objects, and that gave a lot of people the idea that you might be able to use radio to detect metal objects. So the next sort of hero of the story is Marconi. So Marconi was an Italian who moved to England at the beginning of the 20th century. And Marconi was the person who really invented radio communication as a way of kind of transmitting information around. Marconi founded a company called the Marconi Company, and the Marconi Company actually was the first company I actually worked for. I worked for them for several years before things got a bit sticky and I moved on to another company. But Marconi invented radio communication, and Marconi also proposed the use of radio to detect ships in fog, because ships were having all sorts of problems, crashing into each other in fog. The Titanic crashed into an iceberg, largely because they couldn't detect things very well at a distance. The only way they could detect things was by seeing them, and in fog you couldn't do that. And Marconi knew that radio waves would go through the fog, and so he came up with the idea that if a ship transmitted radio waves constantly, then they might be bounced off other ships, and you could then detect them. So he came up with this idea, and it was actually used quite early on in a French ship called the Normandy, which is up there. That's a poster for the Normandy. The Normandy was, the state-of-the-art, the latest ship around, so they decided to put this device in it. Another kind of hint that radar might actually work was that, again, in the 1930s, they set up commercial radio stations. Some of you might have seen the King's Speech. Has anyone here seen the King's Speech? Okay, the King's Speech is all about George VI standing up and giving terrible speeches because he stammered, and then going on the radio and giving terrible speeches because he stammered, and then being trained to how to give proper speeches. And this was all because of the invention of radio as a transmitting device for broadcasting to the nation. And bottom right, sorry, there's a picture of Alexandra Palace, which was one of the first radio stations for broadcasting that was sort of set up. And people started complaining. And the reason they complained was they would be listening to the king or something, and suddenly their signal would fade away and be unreadable. And they realized, the post office realized, this was because aeroplanes were flying past and disrupting the signals. And so the post office wrote a big report on this, which then got put away and forgotten about. But that was in 1933. But that, in a sense, was the first hint that radio could be used to detect aeroplanes. So that was kind of the predecessors of radar. But radar really got going, as I said, in about 1935. Now, one of the people that appears on the King's Speech is a guy called Stanley Baldwin. And Stanley Baldwin was Prime Minister, and Stanley Baldwin was paranoid about bombers. He felt that if there was a war, a lot of people knew that a war was likely against Germany, that if there was a war, then bombers would come over from Germany, bomb London flat, and there'll be 1 million casualties. They were really predicting this. He was really frightened, and he made a speech in the House of Commons in 1933, and his speech said the bomber would always get through. So he appears on the King's Speech if you look out for him. And so the British did what you always do in these circumstances, which is you set up a committee. Okay, so they set up a committee called the Defence Committee, and the guy that was chairing this committee was the guy in the picture. This is Sir Henry Tizard. And Henry Tizard was one of the great scientific civil servants. He worked in the civil service, but he was a very fine scientist. And his committee was really very small. It had on it a guy called Rowe, another one called Blackett, who after the war became a Nobel Prize-winning physicist. He was partly involved with the invention of the transistor, and another guy called Wimperis. And the Defence Committee was set up with the express purpose of preventing Britain being bomb flat in the case of a war. Okay, that was their idea. And they came out with a possible idea that if Britain could develop a kind of a sort of death ray, a radio wave which was strong enough, they could point it at a bomber that would kill the pilot and the bomber, and the bomber would then crash and everyone would be fine. Well, apart from the pilot of the bomber, of course. So they came up with this idea, and they wanted to see whether it would work. So the person they asked to see whether it would work is a guy called Robert Watson Watt, or Sir Robert Watson Watt. Now, I should say this guy is a real hero of mine, and in tribute to him, I have actually kind of dressed up a little bit like him for today. So this is my Robert Watson Watt look, okay? So this is why I'm wearing a tie. Okay, this is very, very rare for me, and my son always points out that I'm losing my hair and going bald just like Robert Watson Watt, and of course I've got the specs as well. So there we are, the Robert Watson Watt look-alike competition, and he was a true British boffin in the best sense of the word, and his background was he was interested in studying, originally he was studying what's called the ionosphere, which is the top part of the atmosphere, which is where it's sort of above where all the weather is, but where lots of electrical activity is. And the ionosphere is very, very important in terms of transmitting radio waves. So he knew all about the ionosphere and the way radio was affected by the atmosphere. And he was working in a place called the National Physical Laboratory. And so he was asked by this committee to do the calculation about radio waves because they knew he knew something about it. So he did a calculation to work out how much power it would require to fry the pilot of a bomber, and he came up with the answer of 5 gigawatts. Now, just to give you an idea what 5 gigawatts means, 5 gigawatts is approximately the amount of power required to power the whole of Wales. 5 gigawatts is approximately the amount of power produced by 2 nuclear power stations, or it's substantially more than all the power generated by all the wind turbines in the UK. It's an awful lot of power. Even today, we couldn't shove 5 gigawatts up into the air, nor would we really want to. So he said, forget it. You're not going to be able to fry the pilot. However, I have got another idea. And what he'd done was he'd asked one of his colleagues, a guy called Wilkins, and we'll meet Wilkins in a minute, to do another calculation about whether radio could actually be used to detect an aircraft. If you put a radio wave up into space, whether it would bounce off the aircraft and can be detected. And Wilkins did a calculation, and in many senses, it was a true back-of-the-envelope calculation. We really suspect he did do it on the back of an envelope. It was that sort of calculation, and I'll show you it in a minute. And he handed it over to Robert Watson Watt, and it was very promising. He felt, yes, this shows a scheme by which you might be able to detect aircraft. Now, like all true scientists, he didn't really believe the answer. No scientist ever believes a mathematician, I can assure you. They always want to check something. And he thought that Wilkins had probably got it out by a factor of 10, but even then he thought it didn't really matter, it would still work. So that's why he was worried by a factor of 10. Okay, so what he then did was he wrote to the committee, and this is a very famous letter. Most inventions, like the wheel or fire, you can't say when it was invented, but we can say absolutely when radar was invented. It was invented on the 12th of February, 1935. And this was the letter that Watson Watt wrote to Rowe, who was on the committee. And this letter is called the Birth Certificate of Radar, because in it says, it was a letter which went with a report, and it says, you know, I've thought very hard about it, we've done a calculation, and we reckon we can detect aircraft using radio waves. And if you look on this letter, if you look hard, there's this wonderful sentence. It turns out so favourably that I'm still nervous as to whether we have not got a power of 10 wrong. Okay, so he thought he wanted to hedge his bets a bit, you know, true civil servant. I wish modern civil servants are quite as honest. So he reckoned he might have a power of 10 wrong, but he still felt that it would work even if he got it wrong, and I'll explain why in a minute. So that's a letter, and that was submitted to the panel, this commenced committee, on the 12th of Feb. And he did lots of other things besides. This report essentially showed that radar would work, what the best wavelength was for it, how you could estimate range using radar, and also the best way to display it. Amazing document. So let me tell you a bit about Wilkins's calculation, because the next couple of slides are a bit hairy-scary, so be warned. But I thought it might be nice to show the mathematical mind in action, as it were. So Wilkins had this idea. Wilkins reckoned that an aircraft has two wings, okay? One wing there, one wing there. And the sort of radio antennae that were being used at the time, and are still used today, are things called dipoles. And a dipole comprises two wires, one there and one there. And you can see these all over the place for Wi-Fi systems and so on. And Wilkins thought, well, maybe an aircraft with its two wings would behave the same way as a radio antenna with two parts of dipole. And the thing in the box underneath, which looks rather scary, is the formula, which was quite well known. It goes right back to Marconi, for the strength of the radio wave that comes out of a dipole. They knew if you put current into the dipole and you were a distance r away from the dipole and your angle to the dipole was theta, then you could calculate the strength of the radio wave, and the strength of the radio wave is the thing in the bottom right of that big orange box. Okay, it's a scary formula, but the nice thing is that formula uses sines and cosines, which I hope you've met in your studies, and not much more than that, and it allows you to predict very accurately how strong a radio wave is coming out of an antenna. So Wilkins knew if you put current into an antenna and it went a sort of few miles up into the air, how strong it was when it got to the aircraft. So there's Wilkins, top right. So there are various things that he did. I don't need to really worry about all the things in this. This is actually more or less taken from the report that was written to the committee. What Wilkins first of all did was he said, suppose you put 1 amp of current into the dipole, then he worked out that the field that got to the aircraft, which he reckoned would be about 6 kilometres away, would be 14 millivolts per metre for every amp. And actually that's quite a high field. 14 millivolts is quite detectable. That would then cause the aircraft's wings to have a current in them. The aircraft wings would then act like a radio antenna and would reflect the signal back. And when the signal got back, the field that you receive would be 15 microvolts per metre for every amp in the current into the aerial. He then reckoned, well, a modern transmitter like the one at Alexandra Palace can put about 15 amps into the dipole, and that means that the received field is 225 microvolts per metre. Now, just to give you some idea of order of magnitude, when you listen to your radios at home, the sort of field that they are detecting to listen to the radio stations is between 1 and 10 microvolts per meter. Okay? Wilkins showed that the received signal at the antenna from this kind of radar system was more like 250 microvolts per meter. So in other words, it was 20 times bigger than could be detected with a normal radio. And that's why he was so confident this system would work. Watson Watt was worried that he got a factor of 10 out, but even if he got a factor of 10 out, it would still be twice as much as could be detected. In other words, Wilkins showed that it was absolutely certain that if you put a radio wave up into the space and it bounced off a bomber, there's a picture there of a bomber, that was the one they used at the time, that was called a Hayford bomber, it would bounce back and could be detectable. And the things in the 3 boxes are the 3 calculations he did for the amount of energy that would get to the bomber, the amount of energy that would then be radiated from the bomber, and the amount of energy that would be detected. And any decently competent mathematician like him should be able to do that on the back of a reasonably large envelope, which is what we think he might have done. It turned out that he was entirely right. He hadn't got a factor of 10 wrong, and exactly this kind of field was going to be detected. So that was his calculation. I would argue that that was one of the most important mathematical calculations ever made. It's not important in the sense that it was groundbreaking research, that it opened up a new field, or that in a sense it was particularly difficult, but it was important in that it completely changed history, that one calculation. Anyway, so the Defence Committee was impressed by this calculation. Tizard, as I say, was a scientist. He knew what was going on. And he went to a guy called Hugh Dowding, who's another kind of hero of mine. I'll tell you a bit more about him later on, who was at the time in charge of that part of the RAF responsible for scientific developments. And Hugh Dowding, moving remarkably quickly for a civil servant, immediately allocated £10,000, so I suppose that'd be almost as much as £1 million now, to conduct experiments into turning that formula into a practical device for detecting aircraft. And so the upshot was, in the 26th of February, which was only 2 weeks after they got the letter, it was moving unbelievably fast. I mean, no government committee, now it would take 2 weeks just to, work out who might be on the committee. They actually got the whole thing going. And I think the reason was that they knew absolutely if they didn't get this right, they were going to lose the war. They started this experiment. So what they did was they got a bomber, which was one of these rather elegant biplane bombers, a Hayford bomber, to fly close to the radio transmitting masts at a place called Daventry, which actually isn't that far from here. This was one of the main broadcast stations. And they would then set up a receiving station. You can see what they had. They had a van with a couple of wires attached. And the bomber flew close to the station, and sitting in the van, they were able to measure the reflected signals off the bomber and detect them and show quite clearly that you could detect a bomber by this process. And if you go to Daventry, which I say is not very far from here, you can see a plaque with their names on it, Robert Watson Watt and Wilkins, who did the experiment, and there's even a picture of the bomber on it as well. So that showed them that it would work. And then, having demonstrated it would work, there then started an absolutely furious amount of activity. So the mathematics showed it would work in theory. This experiment showed it would work in practice. What they then had to do was convert all this mathematics into something which would actually be usable in defending the nation. So what they did was they went over to a place called Orford Ness, which is on the east coast of the UK. It's in Suffolk. And they took up residence in a manor called Bawdsey Manor, and did all their experiments in huts. You can see one of the huts there with post office technology valves. The reason they went onto the east coast was twofold. One was because it was kind of miles away from anywhere, so they could do their experiments in secret, and also because it was close to the North Sea, which is where they reckoned the Germans would come in from, and therefore they could use it to detect the Germans. So they did lots of experiments, and they were joined by a guy called Taffy Bowen, who's bottom left, who's another great hero of mine. Taffy Bowen was one of the engineers who was responsible for taking all this sort of theory that was coming up and turning it into a practical device. And one of Taffy Bowen's ideas was that you could use radar to detect the range of an aircraft. And the idea is breathtakingly simple. If you want to see how far something is away in this room, I might clap my hands and listen to how long it takes to get the echo. And then if I know the speed of sound, that tells me how far away it is. What they did with radar was they sent out a pulse, a very short pulse. That would then go out, bounce off the aircraft, come back. They'd measure the time, they'd multiply by the speed of light, and that tells you how far the aircraft is away. Very simple idea, but worked very well. And that was largely due to people like Taffy Bowen. So these experiments went on at a furious rate. And by 1939 again was 4 years after this calculation, and an astonishingly short time, they came up with a practical system to defend the UK with. Again, nothing now would happen in 4 years. In 4 years, we'd just about be getting the reports back on what we'd done. But they set up a thing called chain home. So these are the masts that they use for chain home over here. When I worked for Marconi in Chelmsford, the laboratories that I worked at had one of these big masts in there, and I asked what the mast was for, and they said purely so everyone knows where the laboratory is. Okay, well, they'd stopped using it, but it was kind of listed by them. These were the masts that they used. They set these up all around the country, facing the Germans. They were called chain home. They worked on quite a long wavelength of about 13 metres, which I suppose is about the width of this room or so. And they had about 20 stations operational when it was switched on Good Friday 1939. So, of course, Good Friday is next week, so that's another kind of link in with what we're doing now. This station had 100 miles range, so it could detect aircraft 100 miles away, and given that most aircraft at the time were flying in at about 200 miles an hour, that gave 30 minutes warning. Now 30 minutes warning was vital because it took about 30 minutes for the Spitfires and Hurricanes that were to defend the country to take off and climb to a height which was high enough to then be able to intercept the bombers. And that 30 minutes was absolutely what they needed. Even then, it was only just barely what they needed to get into a position they could intercept the bombers from. So that was chain home. So these masts, at the bottom of the masts were huts, and in the huts were operators, and the operators were more often than not women in the Women's Air Force, the WAAF, and they had to operate these devices under the most extreme conditions possible, typically being bombed by Stukas and so on. So women in the Royal Air Force played an absolutely crucial role in defending this country. Okay, so these masts are rather interesting. They have a bit at the top and a bit at the middle and a bit at the bottom. We used to call it Nelson's hat when I was working underneath them. And they had these 3 bits for a reason. And the reason was that one of the key things you need to do when aircraft are coming into attack is you need to be able to find the height. And this is how they found the height. Again, they use mathematics. The first calculation is if you can measure that the angle that the aeroplane is to the horizon and bring in the curvature of the Earth, because that's important, and you know the range, and you can measure the range using these pulses, then the formula in the pink box gives you the height of the aircraft. This is the original formula they used, and what's marvellous, nowadays everything's boring, we do it all in metres. In those days things were a bit more elegant. The height was in feet and the range was in nautical miles. and if you combine all those together, you get, and of course the angle has to be in degrees, you get that formula for the height. So that's a nice, again, back of the envelope calculation. For those of you who are interested in these things, this is one of the 101 uses of a quadratic equation, which you can read about in my forthcoming book on quadratic equations. So this is a quadratic, in case you thought quadratic equations were rubbish, that was one of the uses for them. So if you can measure the angle that the aircraft's coming in at, then you can measure its height. And the way they measured the angle was they would measure the strength of the radio wave at different heights on the radio mast. That's why they have a bit at the top, bit in the middle, bit at the bottom. And the thing in the orange box is a formula which tells you if you can measure the relative strengths of the two signals at the top and the bottom, then you can actually work out the angle from that. And that box might look a bit scary. To say how scary that box is, this was a formula which was actually having to be used by these poor WAF personnel in the office at the bottom of the radio whilst being bombed by bombers. So you might think it's pretty nasty doing maths in your classrooms with the teacher looking at you. They had to do it under somewhat more nasty circumstances to use that formula. If I can just talk personally, again, mathematical formulae are fine, but in any real-life situation, you normally have to worry about other things as well than just the formula. You need to worry about extra reflections and the effect of extra bits of geometry. So these formulae were always fine-tuned by flying aircraft at the stations and calibrating it. And one of the things my grandfather did during the war, because my grandfather was a radar engineer during the war, was to fly in things called Avro-Ansons, which were kind of communication aircraft with lots of radio systems, and he helped calibrate all the chain home systems to get the height calculation right. So that's how they estimated height. So in 1940, we had a radar system which could detect the height of aircraft, could detect their range, and could detect them 100 miles out. And we had it just in time for the Battle of Britain. So another anniversary last year was the 70th anniversary of the Battle of Britain. The Battle of Britain was fought between about 600 RAF fighters, 2,000 Luftwaffe bombers and fighters. It was at a time when the person in charge of the whole RAF was Hugh Dowding. This is the same guy that had essentially funded radar, and now having funded it, was in charge of using it. And Keith Park, next to Dowding in this picture, was the guy in charge of the fighter aircraft over the southeast of England. So he was the one mainly in charge of fighting the battle. The battle was fought, say, between Luftwaffe bombers and RAF Spitfires and Hurricanes. Chris Howells, who is one of the organisers of Meet the Mathematicians, comes from the University of Southampton, and it's nice to say that the Spitfire also comes from Southampton. So well done, Southampton. And Dowding was one of the people that also funded the Spitfire. Now we have an interesting thing, interesting contrast between Germans and British people, and I hope I'm not insulting any Germans in the audience. The Germans were fantastic engineers, and they also invented radar, and they designed radar which was really, really accurate, but could only kind of direct one aircraft at a time. And they assumed that the British would be like that. What the British had instead were loads of radars, which were all kind of, some were more accurate than others, made lots of mistakes, but could direct the whole of the fighter force in one go. And the Germans didn't realise that we could do this, and therefore they dismissed radar. They said radar wouldn't work. But they had not realised how it was going to be used. And this is a system that Dowding set up, and it's another nice, lovely application of mathematics. What Dowding set up was what's called a fighter control system, and what he did was he had what's called a filter room, which was in a place in North London called Bentley Priory, and the filter room took in information from all the radars across the country. And the radars were not particularly accurate, and they were combined with literally little old men looking at aeroplanes that were even less accurate. And so it took in lots and lots of slightly inaccurate information. In the filter room were mathematicians. And the mathematicians were looking at where the aircraft were and how they were moving. They were doing calculations as to where they thought the German bombers would be and the British fighters would be. And what they did was they combined their calculations of where they thought the aircraft would be with these data points coming in from the radar. And by combining their predictions with the data, they were able to very accurately work out where the bombers were. And this is now used quite a lot, this idea of combining predictions with data to get something much more accurate. Your mobile phone uses this technology, and GPS uses this technology. And it all goes back to the Battle of Britain. So the filter room worked out where the bombers were. That passed the information on to group. In group, they then worked out how to intercept and then passed it on to the squadrons. And then the squadrons sent the Spitfires and Hurricanes up to do the interceptions. This is the sort of calculations they had to do. Again, if you think Pythagoras' theorem and trigonometry is rubbish, and why are you bothering to learn it? One of the things they had to do was if a bomber was coming in at a certain angle and they knew where a Spitfire was, they had to tell the pilots in the Spitfire what angle to fly his plane at to intercept the bomber. And they had to do trigonometric calculations on the fly. Tizard came up with a formula for finding the angle, which was called the Tizzy angle. And then that was, all these sums were done very, very quickly without using calculators to direct the Spitfires onto the bombers. And this was a typical operations room. This one's still around. It's in Uxbridge. And what they did was they took all the information from the filter room. They fed it through to people on the ground who were typically, again, these women, members of the Royal Air Force, who would move flags around to show where the bombers were, and then the fighter controllers would use those to direct the bombers. It's a bit different from the modern graphical display screens, but the idea was right. And of course the Battle of Britain was won, and Churchill immortalised the pilots with the phrase, "Never in the field of human conflict was so much owed by so many to so few." But Churchill was also fully aware of the importance the radar played, and in fact was very scientifically literate. Well, radar moved on. One of the problems with the radar systems in the Battle of Britain was they used a very long wavelength. And the trouble with long wavelengths is that they don't give much resolution. They kind of gave a very blurred picture of where everything was. They weren't very good at finding the direction of the radio of the aircraft, and they were prone to lots of interference from the ground. And more mathematical calculations showed that radar would work much, much better if you used a much shorter wavelength. The smaller the wavelength is, the more detail that you can see. And they reckoned that they could do it using much smaller wavelengths, like about 10 centimetres. That's about that much. The problem was they couldn't generate radar waves at the right sort of power with the technology at the time, which were things called klystron valves. So they were stuck. And this is where the University of Birmingham suddenly became important. So if this technology works, yes, there we go. So let me tell you about this thing. 1940, two guys called Randall and Boot, who were scientists working here in the University of Birmingham in a lab run by a guy called Oliphant, came up with an idea for generating radar waves. And their idea was to combine electricity and magnetism. If you have a magnetic field, then electrons spin around that field. There's a sort of picture of them spinning round. And as they spin round, they generate very high frequencies. And what Randall and Boot thought was that if they could kind of put a very strong magnetic field and put lots of electrons into that field, they would all spin round in such a way that they might generate very high frequency radio waves which could be used for radar. And so they built a thing called, they called it the magnetron. And they called it a cavity magnetron because it had a hole in the middle for the electrons. And on the top right, we can see the original cavity magnetron, which was actually invented and built in Birmingham. There's a bit of red at the bottom of it, and that's the sealing wax that was used to glue it together with. It cost not very much. It was something like £100, one of the best £100 ever spent. And the cavity magnetron could generate kilowatts of power at short wavelengths. And the cavity magnetron was then used for the rest of the war to generate all the radar waves that were needed. What I have here is a cavity magnetron which my grandfather gave to me just before he died. And this was an original one taken from a Lancaster bomber. And that was one used during the war. The radar waves came out of here. This bit was used to power the device, and the magnet was stuck on the top and the bottom there. See, the little arrow there means it was used during the war. CV is V for valve, saying how it worked. So that's a magnetron. Tizard, the same Tizard that chaired the Defence Committee in 1940, accompanied by Taffy Bowen, who we heard about earlier, took this cavity magnetron to the States in 1940, essentially to bribe the Americans into entering the war. The Americans were extremely impressed and set up their own laboratory in a place called MIT, which some of you might have heard of. That was called the Radiation Lab, and that lab then went on to develop radar in the US. The same mission, this is called the Tizard mission to the US, also took over the jet engine and all our atomic bomb secrets. And again, the atomic bomb secrets, believe it or not, largely came from the University of Birmingham. So University of Birmingham played rather a major role in winning the war. All the stuff went over in a black box, hence the use of the word black box nowadays. So that was used to bribe the Americans, and more or less it worked. So let me tell you a bit more about how radar then went on in the war. These high-frequency radars were then put into aircraft. On the top, we have a Bristol Beaufighter made in Bristol, which is where I live. And Bristol Beaufighters had these very short wavelength radars and were able to detect German bombers in the air and were largely responsible for stopping the Blitz. The German radar worked on a much longer wavelength because they didn't have the magnetron. So the German aircraft below, its radar waves, radar antenna at the front, much, much bigger, which meant they were much, much less effective than the British ones. So that's the Beaufighter. Radar was also used to detect, they put it in bombers to look downwards to see where everything was. Is anyone here from Malvern? Fantastic. Well, Malvern played an amazingly important role. What they did was take the ideas that people had come up with, put them, and in Malvern they set up a research laboratory run by Rowe, who was the same Rowe that was on the committee for the Defence Committee, and they developed ground-looking radar, and the laboratories that were used are still there today. They're now owned by Kinetic. And they developed a system which was called H2S. The reason it was called H2S was that laboratories were visited by the chief government scientific advisor, and he really liked the radar system, and it said it stinks because it hasn't been invented before. So they thought, well, if it stinks, we better give it a smelly name, so they called it H2S. Of course, the problem then came when the scientists visited again and said, why have you called it H2S? And they came up with the idea that it was called height-to-surface radar, but the real reason was for that. And the guy that invented that was a guy called Blumlein, who sadly died during the war in a plane crash. The Germans, of course, were also busy with radar, and again, they had a very different approach. The British approach was rather rough and ready. The German approach was to have very, very highly engineered radars. The disadvantage of that was they could only control one aircraft at a time, and also that they were very expensive to build and modify. And they had two systems, the Freyr radar for long range and Würzburg for short range. And R.V. Jones, who was the chief British scientific spy during the war, using code intercepts made by the Bletchley Park, worked out what the Germans were doing, and they sent commandos in to capture it at a place called Bruneval, and they captured all the German radar and worked out how to then countermand it. And one of the ways they did that was they jammed it using things called chaff or window, which were small amounts of metal. Another big use of radar during the war was in navigation, and that was, again, used a system called oboe. And what was, again, interesting about these navigation systems was they had to build in the curvature of the Earth to do it, which brought in an enormous amount of extra maths as well. So mathematicians were heavily involved with that. Just to conclude, radar, after the war, went on to do many things. A guy called Hay was partly responsible for detecting German jamming, and he was trying to work out a typical why certain radar systems were jammed, and realised that they were being jammed not by nasty Germans, but by the sun. And he realised that the sun emitted radio waves, and his work, combined with Bernard Lovell after the war, led to the invention of radio astronomy. And the guy in the tie in front of the Parkes radio telescope in Australia is none other than Taffy Bowen, who was the guy responsible for developing radar in 1935 onwards. And a further major use of radio and radar technology, very important to our homes, is the microwave cooker. And the microwave cooker, illustrated, has one of these magnetrons in it, and you're using one of those every day. You press a button in the microwave cooker. So modern technology, radio astronomy, all of modern radar, the microwave cooker, and everything else that we hold dear to our lives all came from radar, and radar all came from one calculation back in 1935, probably on the back of an envelope. And I think we have a lot to thank those mathematicians for. Thank you very much.